You may not realize this, but what we call temperature is actually a measurement of molecular motion and vibration. We tend to think of the temperature of a pot of water on the stove as being pretty much uniform throughout, but nothing could be further from the truth. On a molecular level, a pot of water will have molecules in it that range from being very cold to being boiling hot even before you get that pot of water to the stove. All that you are measuring with a thermometer is the average temperature. The different specific temperatures going on inside are arranged according to what is called a Boltzmann distribution curve, and that distribution is what changes with heating. This may seem very complicated, but really it's quite logical. Let's look at the simple case of pure water. Molecules are bumping into each other at random. A chance head-on collision will slow down a pair of molecules, but other glancing interactions can speed them up, depending on the angle and the velocity. In scientific terms, this is called the molecular kinetic energy. Water will evaporate slowly at room temperature, but you can't see it because you can't see individual molecules. As water heats up, the average molecular speed increases, and when the water gets close to 100 degrees Celsius, so many molecules, those that are at the far right of that Boltzmann distribution curve, now have enough energy to escape the surface of the liquid that you can visibly see them as steam. Now let's consider a standard laboratory distillation of salt water. As the water reaches 100 degrees Celsius, vapor begins to make its way up the neck of the distillation flask. The salt is completely left behind because salt cannot become a vapor until it reaches over 800 degrees Celsius, and we're not even close to that temperature. So what we get out is pure water. This is probably the way you thought distillation always works from what you learned in high school science class. In fact, it never works this way in cooking, as you will see in a couple of minutes here. At this point, you might be wondering why I'm talking about distillation, because you're in a kitchen, not a liquor distillery. Maybe you haven't thought of it before, but when you simmer or boil any pot of liquid, you are distilling it. Only instead of condensing the vapor and keeping the liquid that escaped, you're releasing the vapor into the air. Those clouds of steam coming off of your food fill your home with aromas, but there's only so much flavor in any given amount of food, and the sad truth is that the more you can smell when it's cooking, the less flavor will be left in the final dish. That principle was the inspiration for sous vide cooking in sealed bags under vacuum. But that's another topic for another video. Right now I want to stay focused on what happens during conventional cooking. When you cook any stock or sauce in a pan on top of the stove, there are two destructive forces at work. Technically speaking, they are azeotropic distillation and unwanted side chain reactions. I'll explain what each of these means to you. First, let me say, don't feel overwhelmed and give up now. These are just words. The ideas behind them are actually pretty simple, and once you understand what's going on at the molecular level in food, you'll be able to make much better decisions about how you cook things. So what is an azeotrope? Let's go back to the distillation example. Only this time, instead of salt water, let's distill a mixture of alcohol and water. Now a funny thing happens. No matter how carefully and slowly you attempt to distill this mixture, the absolute best separation of the alcohol you can ever hope to achieve still has about 5% water in it, and that's for a very carefully controlled distillation. If you were just to heat up an open pot of alcohol and water to a rolling boil, you'd get almost equal volumes of alcohol and water steaming out. We say that alcohol and water form an azeotropic mixture. That's not some bizarre exception either. There are entire books that catalog known azeotropic mixtures, and millions more that aren't even documented. But why does this happen? Two reasons. First, in the case of water and alcohol, they have somewhat similar boiling points, certainly much closer than water and salt do. As you heat up a mixture of alcohol and water, both of these molecules are mixing together in the vapor. The second reason is what's called hydrogen bonding. Earlier in this video, I explained how water sticks to itself because of weak magnetic forces. We say that water is a polar molecule because it has one strong electronegative atom in it, oxygen. But so does alcohol. In fact, water tends to stick to just about any molecule that has an oxygen or nitrogen atom in it, and that describes just about every flavor molecule known to man. The molecules that we perceive as flavors and tastes because of the olfactory glands in our noses nearly all form hydrogen bonds with water, and many of these are azeotropic mixtures. So when steam comes off, it carries flavors with it. That's why you can smell what's cooking. So what can we do to minimize this loss of flavor? The easiest and most obvious thing is to put a lid on what you're cooking. In organic chemistry, this is called a reflux. As molecules escape the surface of the liquid, they cool off and condense into droplets. Then gravity draws them back down into the boiling liquid beneath them. In cooking, it's called a braise. It's a very useful technique, but it doesn't fit every situation, and you are limited to about 100 degrees Celsius as the actual cooking temperature inside of your braising dish because foods are mostly water. You can increase the temperature above 100 Celsius a bit by increasing the pressure. And indeed, a pressure cooker is an outstanding tool to have in your arsenal, but again, it's not applicable to every situation. What would Chef Ramsay do? Yes, one way to minimize flavor molecules from escaping is the extremely rapid cooking at a high temperature over charcoal. Even though the food is gushing out steam, it only does so for a very short time, and less time means less flavor escaping. Plus, you get the added flavor that the Maillard reaction creates. But charcoal grilling isn't how people cook most things, at least not in this age. What about deep frying, you ask? This may come as news to you, but deep frying causes a lot of steam to pour out of food too. In fact, if steam isn't pouring out, that's when deep fried foods become greasy. It's the steam that's escaping that keeps most of the oil back. The flavor molecules that escape with that steam mostly get trapped in the oil, where they slowly burn and polymerize into carcinogenic gunk, basically. But even if that wasn't true, good luck cooking a soup or a sauce by deep frying it. No. Like the other cooking methods I've listed here, deep frying is an invaluable tool, but it is limited application and can never replace simmering or boiling. And stovetop cooking is still the most common task in any kitchen. This is where the judicious control of heat will determine what comes out tasting like a skilled professional chef cooked it and what tastes like a rank amateur tried to imitate it. The purpose of this entire video is to explain why heat management is essential to the quality of cooking. Now let's go back to the dreaded Boltzmann distribution curve again. Knowing what you do now, you can see that the lower the temperature you cook something at, the fewer flavor molecules will escape. But nothing gets cooked in the refrigerator, so we must find a happy medium where the food gets cooked, but not so hot that all the flavor molecules are fleeing like rats from a sinking ship. Now we come to the second enemy of simmering and boiling: unwanted side reactions. In organic chemistry, this means a reaction that leads to some percentage of products that you didn't want. You try to minimize this by selecting an optimum temperature, but because of the Boltzmann distribution, it's impossible to have a completely uniform temperature in any solution, so there's always some amount of undesired products. And this problem is under controlled conditions with only a couple of reactants. In food, you're dealing with thousands of compounds at once. So, we try to avoid these problems by using the lowest temperature that we can. That'll minimize side reactions, and flavor molecules will be prevented from escaping. And just to be extra safe, we'll keep a lid on it. Does that sound like a cooking process you've heard of? Yes, a crock pot. Now you have the opposite problem in most instances. Sure, the temperature's pretty low, but the reaction time is really long, and if you put more than one type of food in the crock pot at the same time, the resulting side reactions kind of smear the flavors together into a mess, and you get very poorly defined flavors that kind of cancel each other out. A crock pot is fine for a single ingredient, but certainly not a complete meal. Unless you want everything to taste like, well, it came out of a crock pot. Make conscious choices about the cooking methods you use and always aim for the optimum temperature at which the food will get cooked without losing flavor. When it comes to reducing sauces and stocks, a full boil of 100 degrees Celsius is rarely the best choice. Remember that liquids will evaporate slowly even in the refrigerator. A simmer in classic French cuisine often means a temperature of 60 to 70 degrees Celsius, and if something takes 4 hours to reduce at 60 degrees, the result will almost certainly be much better than having reduced it at 100 degrees for 20 minutes. Next, keep in mind that a thin watery liquid near the boiling point, say 90 to 95 Celsius, will practically stir itself because of the motion of convection. But If you have a thick liquid like a reduced sauce that's well below the boiling point, say 60 degrees, it's going to be cooking hotter at the bottom and sides of the vessel than it is in the middle, so you need to stir it frequently to keep it from burning. The rule is, the thicker the liquid, the more unevenly it will want to cook. Next, the flavor molecules in foods are prone to reacting with each other during prolonged cooking, and even something as seemingly simple as a boiled carrot contains a vast array of flavor molecules capable of reacting. Each reaction that occurs makes it taste less like a fresh carrot. Sometimes that's a good thing, but often it is not. With very few exceptions, one-pot dishes yield mediocre food. Cook segments of your dish separately and reduce the time that the components spend cooking together in order to retain bright, clean flavors. Putting everything into one pot is like pouring 5 different colors of paint in a bucket, stirring it around, and then expecting to be able to paint a masterpiece. It just doesn't work that way. Hopefully, I've given you some new interesting insights into the science of cooking. By understanding what's going on, you'll be able to make better choices and produce better tasting food. As always, thank you for your continued support.
Also look for my cocktail book, Cocktails of the South Pacific and Beyond, Advanced Mixology, available through Amazon online.